Okay, y'all, welcome to your final video of the semester, section 9.7. We're going to talk about plane curves and parametric equations. So let x be a function of t and y be a different function of t, g of t. And this t is what is called a parameter. So that says that right down here. T is called a parameter, and so that's where we get parametric equations from. And so the collection of points defined by f of t comma g of t is called a plane curve. The equations themselves are called parametric equations. Now, this is just a new way of plotting points and graphing. And so I'm going to explain this to you. I don't think it's going to be too difficult. Obviously, you guys are more than welcome to ask questions if you need help. But it's going to be basically introducing this new variable called t, which is a parameter, and t is basically how we're going to plot our points x and y. So before we get into an example and I explain exactly what I mean by that, I do want us to look at this note. A couple of important things here. Parametric equations that define a curve are not unique. So what that means is that there are usually many ways to parameterize any given curve or graph. And then also curves defined using parametric equations have what we call an orientation, meaning that the direction is important. And the orientation basically just means the direction that the curve is headed in. So a basic example through this picture here, if we start at t is equal to a, to figure out what the point is where t is equal to a, we would plug a into our function f of t, that would give us our x-coordinate, and we would plug a into our g of t, that would give us our y-coordinate. We keep plugging in values for t, and that's how we get these points. And you can see that we're riding along this curve in this orientation. I don't know if you can see those arrows there or not. Maybe if I zoom in a little bit, you'll be able to see these arrows that tell you the orientation of the graph. So this is just any point that's on this curve, f of t, g of t, and then the curve stops once you get to sort of the upper bound of t, which in this case, this picture just calls b. And sometimes you don't have an upper bound. Sometimes t goes from negative infinity to positive infinity, or whatever the case may be. So let's take a look at this example, and I've gone ahead and drawn a nice little table of values and a graph here. And so as we fill in this table of values, we're going to figure out what x and y are based on the equations that are given. X is equal to t plus 10, and y is equal to the square root of t. And then as we figure out what those values are, we're going to graph them below. Okay, so starting with t is greater than or equal to 0, the first value of t that I am able to use would be t is equal to 0. So if I plug 0 into both of my equations here, what am I going to get for x and y? Well, x is equal to t plus 10. So if t is 0 right now, 0 plus 10 is going to give me 10. And y is going to be 0 because the square root of t, which right now is 0, is 0. So at t is equal to 0, I'm going to plot a point, and I'm just going to pretend like this is the point 10, 0 here, and that's going to be my first point. Now, notice the domain of the parameter t greater than or equal to 0. So we're going to choose any number greater than or equal to 0 to plug into our table here. But I'm going to choose very specific values based on my equation here. So I'm not going to go to, let's say, 37 because I don't know what the square root of 37 is. I'm going to let my t values here be determined by what would be easy to graph. And so the next square root that would be easy to graph would be the square root of 1. And so I'm going to let that be my next t value. And so therefore, x is going to be t plus 10, so 1 plus 10, which is 11. And y is going to be the square root of 1, which would be 1. And so at 11, 1, I'm going to plot my next point. And there is my orientation. I am moving along the curve in that direction. Okay, the next value of t that would be nice would be not square root of 2, because that would be a decimal. Square root of 3 would also be a decimal. Square root of 4 is the nice the next nice one. So x is going to be 4 plus 10, which is 14, and y is going to be the square root of 4, which would be 2. And so that point is 11, so 12, 13, 14, and then up one more. And so I've got my next point, which is here. And so there's my orientation. And obviously I could, keep going here. The next nice number I would pick is 9, and that would give me an x value of 19 and a y value of 3. And so that would be, quite a bit longer down here and then just up a little bit more. And so what you notice is that this looks an awful lot like a square root graph. And so what we're going to do now is called eliminating the parameter. And that's in order so that we can find the rectangular equation of the curve, which is in the form of y equals a function of x. Okay, so what we're going to do here is we're going to solve this equation for x, which is x is equal to t plus 10. We're going to solve that equation for t. So if I subtract 10 from both sides, then I'm going to get x minus 10 is equal to t. And then I'm going to substitute into my equation for y, which says y is equal to the square root of t. However, t I know now is x minus 10. And so here is my rectangular form of this equation. And notice that this is a square root function. It would have been shifted over 10 to the right. And you can see here that, remember, this was the point 10, 0. So this is exactly the graph of a square root function that has been shifted 10 to the right. Okay, letter B, again, I've already got these table of values and a little tiny graph set up here. So we've got x is equal to t squared plus 4, y is equal to t squared minus 2. And this time, t is changing from negative infinity to positive infinity. So what I'm going to do here is I'm going to try to stay around the origin. And so I'm going to have 0 here. I'm also just going to put, some numbers that are close to 0 on the left and some numbers that are close to 0 on the right-hand side as I do this. Okay, so starting with t is equal to negative 2, if I plug that into my equation for x, negative 2 squared is 4, plus 4 gives me 8. And plugging into my equation for y, negative 2 squared is 4, minus 2 is 2. And so this is going to be the point 8 and 2. And so we'll just sort of estimate there that we're talking about that point right there. Okay. Next, we would have negative 1 be our t value. So plugging into our x equation, negative 1 squared plus 4 would be 3. And plugging into our y equation for t being negative 1, that would be negative 1 squared, which is 1, minus 2 is negative 1. And so 3 negative 1 is going to be, let's just say, about right here. And so what I have so far is a line that's going in that direction. And then at 0, I'm going to have 4 and negative 2. So 4 and negative 2. And I believe I might have made a mistake here, just kind of a minor mistake. I believe that number should have been a 5. Yeah, negative 1 squared plus 4 would be 5. So let's say that this point that I plotted just a moment ago, let's say that that is 5, negative 1. And so now we're going to plot the point 4, negative 2, which is going to be a little further over. And so we're still going in this direction. And then when we do t is equal to 1, we're again going to get 5. And we're going to again get negative 1. So what happens is that the graph actually starts to turn around. And it actually starts to go the other direction as well. And so what you are going to end up having is this line that continues on and on and on and on. This point right here, the 4, negative 2 point, is sort of like the dead end, if you will. And so the line starts here and it goes down, and then it turns around and goes back up with a dead end at the point 4, negative 2. Okay, so what we want to do now is we want to eliminate the parameter so that we can write the rectangular equation of this graph. And so we're going to start by solving our x equation by subtracting 4 on both sides. So I'm going to have x minus 4 is equal to t squared. And what I notice is that t squared is exactly what I have to plug in into my other equation. So y is equal to t squared minus 2, and I'm just going to replace t squared with x minus 4 minus 2, which means that y is going to equal to x minus 6. And you'll notice that that is a linear function, and the graph that we put down on our paper is a line, and so that would make sense why we would get a linear equation. Okay, letter C, we're going to do something very similar here. Again, t is ranging from -infinity to infinity, so I'm going to start at the origin and just pick some numbers that are close to the origin on either side of 0. And so you guys can obviously plug into these equations yourselves. You guys don't need me to do that for you. And so here's what you're going to end up getting for your x values, 24, 6, 0, 6, and 24. And for your y values, you're going to end up having 2, 3, 4, 5, and 6. Okay, so plotting those points, 24, 2 is going to be way down here on the right-hand side, 24 and 2. And then 6 and 3 will be a little further back and a little higher than that. So there is 6, 3. 0, 4 will be here on the y-axis. And then 6, 5 is going to be directly above that point that we had before. And 24, 6 is going to be directly above that very first point right there. And so what we have is this sideways parabola, and you'll have to forgive my drawing here. It's not very good, but here's the orientation of this particular graph. And this is basically a sideways parabola. And so when we solve this and eliminate the parameter here, we're actually going to write this as x is equal to a function of y. And so what that means is that I'm going to take my equation for y, I'm going to solve that for t, which is going to give me y minus 4 is equal to t, and then I'm going to substitute that into my equation for t, which is going to give me x is equal to 6 times y minus 4 squared, which in fact is the equation of a sideways parabola. Okay, letter D is going to be fun because it's trig, and this is actually going to be a little easier than you might think since t is only going from 0 to 2 pi. So I'm going to start at 0 and then end at 2 pi, which is going to be, I believe, here. And I'm going to choose really nice angles. And really, the nice angles are the quadrantal angles. So I'm going to choose pi over 2 and pi and 3 pi over 2. Okay, so letting t be 0, x is equal to 7 times the cosine of 0. I know that cosine of 0 is 1, so times 7 gives me 7. And 2 sine of 0 is 0. And so that is going to be 0. So at time t equals 0, we're going to be at the point 7, 0. At pi over 2, I know that, well, let's go ahead and do this. How about we say at t equals 0, at theta equals 0, cosine we know is 1, and y is 0. So how about here we put 0, 1, and then -1, 0. This might help us remember some of these values that we're supposed to know. And then, of course, at 2 pi, we're back to where we started at 1, 0. So for x is going to be 0. Y is going to be 1 times 2, which is 2. And so we're going to be at this point 0, 2 right here. At pi, cosine is -1. So 7 times -1 is -7. And sine is 0. So 2 times 0 is 0. So we're going to be over here at -7, 0. And then finally, well, and then at 3 pi over 2, cosine is 0, sine is -1, so this is going to be -2, and so that will be here. And then at 2 pi, we're going to go back to where we started from. So the way this looks is you start here at t equals 0, and then it makes what is called an ellipse. So an ellipse is what this graph represents. And so it actually turns out that equations of this form always represent ellipses. And there's a vocabulary question about that on your online homework that you'll want to make sure you get correct. So equations like x equals a constant times cosine of t, y equals a constant times sine of t, those are always going to give you an ellipse for the graph. And here's how we're going to eliminate the variable. eliminate the parameter. We're going to solve this equation for cosine of t, this one right here, and we're going to solve the y equation for sine of t. So if I solve x divided by 7 is equal to cosine of t, and y divided by 2 is equal to sine of t, and then I'm going to reach into my bag of tricks for trig, where I know this identity. I know that sine squared of t plus cosine squared of t by a Pythagorean identity is equal to 1. And so that's the identity I'm going to use to eliminate the parameter here. So this is going to be cosine of t squared plus sine of t squared, oops, sorry, that should be a 2, is equal to 1. And then I'm just going to square that out, and I'm going to be done. So x squared divided by 7 squared, which is 49, plus y squared divided by 2 squared, which is 4, is equal to 1. And there is my elimination of my parameter. That is my rectangular equation. Okay, we're going to do one more ellipse, except this time notice that 0 to pi is the interval for t. So this is actually going to be only half of an ellipse. And so starting at 0 and then choosing the quadrantal angles, pi over 2, and stopping at pi, I know that at 0 on the unit circle, I'm at the point 0, 1. I'm sorry, that's not correct. 1, 0. And then pi over 2 is 0, 1. And then pi would be negative 1 and 0. And so when t is 0, x is going to equal to 2 cosine of 0, which will be positive 2. And y is going to be 0. At pi over 2, cosine is going to be 0, and sine is going to be 1, times 5 is 5. And then at pi, cosine is going to be negative 1, times 2 is negative 2, and sine is going to be 0 times 5, which is 0. So we're going to start at 2, 0, which is here, and then go to the point, oh, sorry, that's probably not a good place to put that point, so let's maybe put it a little closer to the origin to make it look more like 2, 0, and then 0, 5, and then negative 2, 0, and that's going to be the stopping place since t stops at pi. And so this is the upper half of this ellipse here. And so I'm going to go ahead and do exactly what I did in an example D, which is eliminate the parameter by solving for cosine of t in the first equation and solving for sine of t in the second equation, and then using a Pythagorean identity. So this is going to be x divided by 2 squared plus y divided by 5 squared is equal to 1. And therefore we have x squared divided by 4 plus y squared divided by 25 is equal to 1. But before we finish, we need to add an extra stipulation because this is only the upper half of the ellipse. And so because it's the upper half of the ellipse, that means the y values all have to be greater than or equal to 0. So I'm going to add on that extra stipulation to basically illustrate the fact that it's only half of the parabola, and more specifically, the upper half. Okay, example 2 and 3, we're going to find two different parametric equations for a rectangular equation. I remember I mentioned earlier in the notes that parameterizations are not unique. There are different ways to find other parameterizations. And so on letter A, we're going to substitute x is equal to t. And so that's my first equation, x is equal to t. Now I just need to find my y equation. And using this rectangular equation here, I know I'm just going to replace x with t, and that's going to be 5t minus 4. And it's literally as easy as that. Now, substituting y equals t is a little bit more challenging. That is already our y equation, which means we need an x equation. And so starting from this, I'm going to have y, which now is called t, is equal to 5x minus 4. And once I solve that for x, I'll be done. So I'm going to go ahead and add 4 to both sides and then divide by 5. And that's going to give me x is equal to t plus 4 divided by 5. Okay, example 3, very similar. We're going to do the same thing. We've got a rectangular equation, y is equal to x cubed plus 3. And in letter A, we want to substitute x is equal to t. So that's just going to be very simply y is equal to t cubed plus 3. And in letter B, we want to substitute x is equal to t cubed. So that's going to give us y is equal to t cubed plus 3. And remember that when you raise powers to powers, you multiply the exponents. And so that becomes t to the 9th plus 3, and that is your answer. Okay, example 4. We're going to be given the graph of a parametric equation, and then we're going to be asked to find the parametric equations that represent that particular graph. So it says that our curve starts at 6, 0. It ends at the point 7, 8, and we want the parameter t to start at 0 and end at 8. Well, look at this picture for me and ask yourself, what else other than t starts at 0 and stops at 8? And hopefully you said the y-coordinates. And so because the y-coordinate starts at 0 and ends at 8, and we want t to start at 0 and end at 8, we are going to define the y-coordinate just to equal to t. Okay, what that means is that once I find my x equation, I'm done. That's all I'm going to have to do to be finished with this problem. And so here's what we're going to do. We're going to write the equation of this line, which is like one of the very first things we ever did in college algebra, was write the equation of a line. And so remember, when we do this, we always start from what's called point-slope form, and we need a point and a slope. So if you just take this point down here at the bottom, that's the point 6, 0, and so this is going to be y minus 0 is equal to, I'm going to leave some room for my slope, x minus 6. And then to find the slope, the easiest way to do it is just by looking at the graph and figuring out the rise over the run. So if I start at this point and I rise up to where my next point is, that is a rise of 8. And if I go over and run, that is a run of 1. And so that's going to give me a slope of 8. And so this is going to be y is equal to, I'm going to go ahead and distribute my 8 and get 8x minus 48. And I know that y is equal to t. So t is equal to 8x minus 48. And as soon as you solve that for x, you will be done. So t plus 48 is equal to 8x. Go ahead and divide both sides by 8. And I'm going to go ahead and split through the numerator for my final answer. So t divided by 8, or 1/8 t, plus 48 divided by 8, which will be 6. And here is my parameterization. Okay, on example 5, if we remember example D and E from earlier on example 1, this is going to be pretty straightforward. So notice that this is the graph of an ellipse. And so we already said earlier that ellipses take the form of x is equal to a cosine of t and y is equal to b sine of t. Our objective then is just to find a and b. And so a is going to be the distance from the origin on the x-axis to the ellipse. And so since that distance is 5, I know that here I'm going to have 5 times the cosine of t. And b is the distance on the y-axis. So on the y-axis, starting at the center, I'm going to go up to 3, and so that's going to be 3 times sine of t. Okay, example 6. This is the end of the notes, and so here we go. We're ready. Find parametric equations for an object moving clockwise. That is very important in this problem. Notice that on example 5, we were moving counterclockwise, and I barely even said anything about that. But here, clockwise is going to become very important, because what that means is that we're going to have to move in the negative direction. Okay, so along the ellipse, x squared over 16 plus y squared over 9 is equal to 1. And so these numbers right here tell me my a and my b, but more importantly, those are already squared. And so what that means is that if a squared is 16, a is 4, and b is going to equal to 3, since b squared was 9. So I know I'm going to start off here with x is equal to 4 times cosine of something, and notice I didn't say t, and there's a reason for that, and then 3 times the sine of something. Okay, well, the fact that we're rotating in the clockwise direction means that this is going to be cosine and sine of something negative, And then the last important piece of information here is that it requires 4 seconds for a complete revolution. And what that's going to tell me then is my period. And so go way back to when we graphed sine and cosine, and we remember that period was equal to 2 pi over b, where b was the number in front of x, or in this case, it will be the number in front of t. So if it requires 4 seconds, then that means that my p, is going to be 4. And then I'm going to solve this for b. So multiply both sides by b and divide by 4. And that's going to give me b is equal to 2 pi over 4, which reduces to pi over 2. And so this is going to be negative pi over 2t and negative pi over 2t. And again, negative because we were moving in the clockwise direction. All right, that's going to do it for section 9.7, and that's going to do it for plane trigonometry. You've got one test and your final exam left, and then the semester will be over. You guys let me know if you have any questions on these notes.